All right, so let's get started. And I'm recording today's lecture because we'll be discussing a lot about the differential amplifiers and also regarding homework 8 and what kind of problems you can expect in the exam as well. So I'll be recording both today's lecture as well as Wednesday's lecture for students who may not be able to join for those particular lectures. Okay, and I'll be posting them on Canvas. So we have been discussing the differential amplifiers for the past few lectures. And as you know that if you are able to see that the differential amplifier is symmetric on the two sides, the left-hand side and the right-hand side looks exactly the same, then I think there's some feedback here. Okay. Yep. So you can apply the half circuit theories, right? So if the left-hand side and right-hand side of the differential amplifier is symmetric, you only need to analyze the half circuit of it. You only need to analyze the single-ended version of it, which you are already an expert at, right? So we have all gone through exam 2, right? So that was your single-ended amplifiers. Now, in terms of the differential amplifier, keep in mind that if your input is differential, if everything is symmetric, if left-hand side you are providing a signal with 0-degree phase, on VIN2 you are providing a input with 180-degree phase, that is, you are applying a differential input, then your point VP is a virtual ground. And we already know what a virtual ground means, that it can have a DC potential, but the AC potential will be 0 at that point. We already looked at what is the differential mode gain and what is the common mode gain of this structure, and how do you define CMRR, which was part of your lab 6 as well. And we know that for this kind of circuit, we can do a half circuit analysis. So your gain is nothing but minus GM times RD, if you can represent it as a common source amplifier in a single-ended fashion, right? That's a half circuit of the differential version that we are showing on the left. If you have a differential amplifier with diode connected load, then instead of minus GM times RD, your RD or the load that is connected to the drain of your M1 transistor, that RD becomes the resistance that you see looking at the drain of this diode connected transistor. So remember that this is a diode connected PMOS transistor. We are connecting the drain to the gate. So be it a PMOS, be it a NMOS, the resistance looking into the drain of a diode connected transistor will be 1 upon GM, right? So instead of seeing RD looking on top, which was here. So here looking on top, you are seeing RD. This resistor value was RD. So instead of that, here you will be seeing 1 upon GM and 1 upon GM of the M3 transistor. So that's how your gain becomes minus GM times 1 upon GM3, or minus GM1 times 1 upon GM3, right? Similarly, if you have a differential amplifier with current source load, instead of having a diode connected load, if you have a current source load, that is, you're using your PMOS transistor as a current source. So you're biasing it in saturation. If this is biased in saturation, the resistance that you see looking at the drain of this transistor will be RO. Right, the output resistance of that particular transistor. That, in parallel with the resistance that you see looking down, is RO of the M1 transistor, right? So you have RO of the M1 transistor in parallel with RO of the M3 transistor. That's your output resistance at one of these Vout nodes. So your overall gain becomes GM1 times RO1 in parallel with RO3. Or if you look at the other half circuit, that is this part, you can also write it as GM2 times RO2 in parallel with RO4. Right, and both are same because it's a symmetric circuit. Whatever half circuit analysis that you do on the left-hand side, the same analysis can be done on the right-hand side. And you can also draw the small signal models to prove all this. But right now, I think all of you have an intuitive feeling of the small signal analysis and what we try to do. We want to find out the effective GM or capital GM, as I sometimes mention it in the class. And you want to find out the effective R out or the capital R out at the output node, and then multiply the two. You multiply the effective GM, you multiply the effect with the effective R out, and then you get the effective gain. So that's the intuitive way of understanding how much gain you should expect from any circuitry. Just find out the effective GM, find out the effective R out, use all your intuitions that you have learned in the class, and your answer will be more or less correct, maybe 95% correct. Okay. And that's good enough for all analog circuitry because there's always some tolerance in the component values. You'll never, if you do hand calculations up to 3 decimal places, you'll never see the exact same value when you are doing the measurements or when you're simulating it. Right? Okay, so we also looked at Diff-Amp with current mirror load. So now this is a circuit which is not where you cannot apply the half circuit theorem, because your left hand side of the circuit does not look similar to the right hand side circuit. But we analyzed it in a different way, that okay, if I have let's say only one of the inputs present, right? So we use superposition in this case. If we have only one of the inputs present, the current that is created in the left hand side branch, that will be GM1 times V in 1, and that current will be mirrored on the right hand side branch, right? This is a current mirror on top. The PMOS configuration that you see on top is a current mirror, right? So what's the job of the current mirror? It will just duplicate the current on the reference branch to the mirror branch, right? So if the current on the reference branch is GM1 times V in 1, the mirrored current on the other side will also be GM1 times V in 1. So it will be the exact same current on the two branches for the case when you have this one of the inputs present. Now you connect the other input as well, right? So you'll see another current, GM2 times V in 2, flowing in this branch. Now, whether these two currents will be added or subtracted, for that, remember that when you are trying to find effective GM, in this case, what you are trying to do, by finding out the currents, you are trying to find out the effective GM, right? If you apply an input, what would be the effective output current, right? That's what you try to find out when you try to find out the GM. And GM, or transconductance, is the ratio of your AC output current to the AC input voltage, right? AC output current divided by AC input voltage is your AC transconductance. That's your capital GM, or the effective GM that we always talk about. Now remember, when you are trying to do that, we always AC ground the output node, right? So when you think about the small signal analysis, or if you think about the very fundamental common source circuit. So what was the basic common source circuit? You had an NMOS transistor here, your source was grounded, your input was provided to the gate, and your output was taken from drain, right? So that was the very simplified version of the common source circuit. And you had some kind of load, let's say RD, connected at the drain. So when you're trying to find out the effective GM of this circuit, you don't want to be biased, or you don't want to be affected by whatever is connected at the load. So in that case, when you're trying to find out the capital GM, you disconnect the load and you connect ground, or an AC ground, to that point. So effectively, you want to short this load, whatever load is present, and you short this to an AC ground. Remember that VDD also is also an AC ground. So just shorting the resistance, the RD resistance, is fine, right? So that's what you do when you try to find out the effective GM. And why is that? Because you don't want to have any effect of your output load on the effective GM. You consider the effect of the output load when you are finding out the R out. So you separate those two out. First, you find out GM, and GM is not a function of your output load. GM is just the transistor's property that you are creating an output current because of an input voltage. Because this is a transistor's property, you don't want to be biased, or you don't want to be affected by the output load. That's why you disconnect the output load, connect an AC ground to that point, and then find out the effective GM. On the other hand, when you are looking at effective R out, then you cannot ignore the load that is connected here. Then you sort of look at what is connected looking towards top, what is connected looking towards bottom, take an parallel combination of those two. That's your effective R out, right? So that's how you find out your effective GM, or capital GM, and your capital R out. So just by applying the same concepts here, what you're trying to do is to find out GM, or to find out what's the effective output current, because that's what you want to do. If you know your effective output current, AC current, divided by the effective input AC voltage, you get the GM, right? Current divided by voltage is a transconductance. So you're trying to find out the current, but remember that you have to AC ground the output node while you are trying to find out GM. And that is true for any analysis that you do in any circuit. Okay? So that's the method you should follow to find out the capital GM. So if you are connecting an AC ground to it, the current that was flowing through M4, that will go to that AC ground, and the current that flows in M2, that will come out of that AC ground, right? So that's why you have the currents flowing in two different directions. That's why you have this subtraction sign. You can also draw the entire small signal model and show that this is correct, But this is how it works if you just try to think about this intuitively. Okay. So what's the total overall current? It's GM1 times V in 1 minus GM2 times V in 2. And remember that if these two transistors are matched, if your M1 and M2 are exactly equivalent, then your GM1 is equal to GM2. So your output node current becomes GM1 times V in 1 minus V in 2. So your effective capital GM, that is equal to small GM1. Because the other quantity is V in 1 minus V in 2, that's your differential input voltage. The differential input voltage multiplied with GM1, that's giving you your output node current, right? So your capital GM or the effective GM is still the small GM1, which is in essence equal to the small GM2. Okay, so what would be the output node's voltage? Now you have your transconductance, which is minus GM1 or GM1 in this case. And since it is a common source stage, we have that minus sign. That multiplied with the effective output resistance, which is RO2 in parallel with RO4. Why RO2 in parallel with RO4? This is your output node, right? What are the two transistors connected here? You have a PMOS transistor connected M4, and you have an NMOS transistor connected as M2. In both cases, you're looking at the drain of the transistor. You're looking at the drain of the M4 transistor, and in parallel, you're looking at the drain of the M2 transistor. So it is RO2 in parallel with RO4. That's your output resistance, right? So what's your overall gain then? Your input transconductance, which is GM1 times RO2 in parallel with RO4. Remember the negative sign because this is still like equivalent to a common source structure, right? So your input is at the gate, your output is at the drain. Okay, so we now have a clear idea about how the op-amp should look like. Your op-amp can have, let's say, a differential amplifier with a current meter load as the first stage. Then you can have a common source amplifier if you want to have more amplification, if you want to have more gain. Because the gain of the differential amplifier with current meter load, we just proved that this is GM1 times RO2 in parallel with RO4, right? Usually, the value of these gains, once you solve the homework problem, you'll see that this gain is only about 20 or so, right? It's in the range of 10 to 20. So this is not very high. Ideally, an op-amp's gain should be infinite, right? That's the ideal op-amp. It has an infinite gain. So how to increase the gain? You just have more and more amplifier stages connected in cascade. So you cascade stages, right? And keep in mind, there's a difference between cascaded stages and cascode amplifier. So cascode amplifier is when you're trying to increase the R out of that particular amplifier, you add one single transistor to it, and then you sort of increase the gain. We'll come to that later as well. But right now we're talking about cascading amplifier stages. That is, you put one stage after another so that the gains get multiplied. If the gain of one stage is A1 and the gain of the second stage is A2, then your overall gain becomes A1 times A2, right? So that's just the concept of multi-stage amplifiers that we have learned before. So this is not cascode amplifier. So that's a different concept. Okay. So if you just have cascaded amplifiers, let's say you have gain of another 20 from the second stage, from the common source stage. So you have an overall gain of 400. And remember that at the end, you have to put a source follower or a common drain stage so that the R out or the output resistance of your op-amp is small. So that was the other property of your op-amp, right? Your input impedance needs to be infinite, your gain needs to be infinite, and your output impedance needs to be 0. Those are the properties of an ideal op-amp. You can satisfy the criteria that your input impedance is infinite because you are only seeing the gates of the devices, and ideally there should not be any current flow into the gate if we are looking at low frequencies, right? So we solved one homework problem where your input impedance was not infinite. So homework 6, where we are looking at the parasitic capacitances and we are thinking about high frequencies. So at high frequencies, the assumption that your input impedance is infinite will not hold true. But for low frequencies, you can assume that since it's going to a gate, it's infinite resistance, your Rin is still infinite, right? So that's all we are concerned about in this course. But for future courses, let's say RF design courses, you have to keep in mind that the input impedance may not be infinite, even if it is going to a gate, because there are effects of parasitic capacitances. But let's worry about that at a later time, not now. Now, so Rin is infinite. Whatever the gain is, let's say 20 multiplied with 20, that is 400. That's pretty high. I would say that, okay, let's consider that to be almost infinite. What is your R out? R out is 1 upon GM, because that's the R out of a source follower stage, right? Source follower stages output impedance is 1 upon GM, because you are always looking at the source of a transistor. So for source follower stage, your input is provided at the gate. Your output is taken from the source, right? So this is where your output is taken from. And let's say you have some kind of a resistor connected here. So that is your RS. So if this RS is sufficiently high, what's the output impedance of the source follower stage? You see 1 upon GM looking at the source of the transistor, and you see RS looking down on the bottom side. So it's a parallel combination of 1 upon GM and RS. If RS is sufficiently high, if RS is high enough, you'll see only 1 upon GM, right? Because a small resistance in parallel with a large resistance is equal to the small resistance. So that's why your output impedance could be lowered. It cannot be exactly 0 as we talk about the ideal op-amp. For ideal op-amp, the output impedance is 0. Here it's not 0, but it's low enough. 1 upon GM is usually regarded as low enough. On the other hand, if you look at the output impedance of the common source stage, or if you look at the output impedance of the Diff-Amp stage, that is RO2 in parallel with RO4 or RO1 parallel with RO2, which is a high value, right? So instead of having a high value output impedance, you're trying to design a low value output impedance through the source follower stage. So that's how you have these 3-stage configuration. So that's all good. Now, what's the problem here? The problem is that there are too many poles in the design in the system, right? So you know that the differential amplifier, whenever you have some kind of RC, whenever you have current flowing through your input, or you have current flowing through your output, you have some parasitic capacitance at the input and the output side. So you always have these RC. So you always have resistances and capacitances at every node. And any RC will create some kind of a pole or zero, right? That's what you know from the frequency response of an op-amp. Now, here you have too many stages. You have a Diff-Amp, you have a common source, you have a source follower. There are so many stages. There are so many resistances, capacitances, parasitics all over the place. What will happen is that there would eventually be too many poles in the system. There is one pole at the input. There would be one pole at the output of the first stage, which is also the input of the second stage. There would be one pole at the second stage output, or the input of the source follower. And also there would be one pole at the source follower's output. But remember, when we were analyzing op-amps, we assumed that op-amps are single pole systems, right? That was our assumption when we were learning about op-amps. So we learned about the open loop gain and the closed loop gain of the op-amp, right? So what was the open loop gain? Open loop gain was A0 at low frequencies, but we also looked at the frequency dependence of it. We added this term and the denominator. So remember, go back to your maybe lecture 8, lecture 9, just before the exam number 1, that we studied the frequency response of an op-amp. And then at denominator, you had this 1 plus JF over F open loop term, right? So that means that at F open loop, you have a pole, and after that, your gain drops. Before that pole, your gain is equal to this AOL, or AO in this case, or whatever you see at the numerator. But after the open loop pole, your gain drops, right? And it drops at a slope of 20 dB per decade, right? Why 20 dB per decade? Because what is meant by a decade? It means by 10 times the frequency. So if you make your frequency 10 times, your denominator becomes 10 times, give or take, because it's 1 plus some large value. You're making that large value even larger, 10 times larger. So your denominator almost becomes 10 times of what it was before. So your overall value of the gain becomes 10 times smaller, right? So if the gain was 100 in the beginning, so if this point is 100, 1 decade away from the pole, the value will become 10, right? Because the denominator will become 10 times larger. So your overall gain will become 10 times smaller. What is the representation of something being 10 times smaller in dB scale? It's 20 dB, right? So that's why if your voltage quantity, this is voltage gain, remember, this is not power gain. So your 20, the definition of dB is basically 20 log base 10 of a ratio, right? So what is the ratio we are talking about here? we're talking about a ratio of 0.1, right? So this is 20 log 10 of 0.1. So what would be 20 log 10 of 0.1? That is -1, right? So if you just put into the calculator, you may not able to remember this all the time. Just put it into a calculator, you'll see that log 10 of 0.1 is -1. Why? Because 10 to the power -1 is 0.1, right? 10 to the power -1 is 1 upon 10, that is 0.1. So that's why this becomes 20 log 10 of 0.1, that becomes -20, right? You're multiplying 20 with -1. So as you're increasing the frequency by 10 times, your gain will be reduced by 20 dB. So that's why we say that it has a slope of 20 dB per decade. So the reduction in gain, that is 20 dB per decade. As you're increasing the frequency by 10 times, your gain drops by 20 dB. So this is something that you have already studied. And also you have looked at the closed loop gain, which is A infinity over 1 plus 1 over t or 1 over tau. And then we found out everything like what is the value of A infinity, what is the value of tau. Tau is basically your A open loop multiplied with beta. That's the loop gain. Whereas your A infinity, that was the gain in the closed loop, assuming that your op-amp has an infinite gain, that just became 1 upon beta, right? So just go back to those notes. It's the same numbers that I'm representing here. So what I'm trying to get here is that we always assume that the op-amp is a one-pole system. You have one pole, and then you have a 20 dB per decade slope. That's something that we are not satisfying here. You have so many poles because of all the RCs in the circuit. So in case of op-amp design, this is not acceptable, that you have multiple poles at multiple points in the frequency. So you have a positive gain, you have a gain which is more than 1, and you have these multiple poles. What is acceptable is that you have the second pole at a much larger frequency when your gain has become less than 1. So this is 0 dB. Let's say that my x-axis, the line for the x-axis or the value of the x-axis is 0 dB. So if your gain is less than 0 dB, which means that the gain is less than 1, at that point, if you have a pole, it's fine, it's acceptable. And we'll see why that is acceptable. Because here you'll see that there is a concept of stability or instability, right? And instability means oscillations. Why oscillations are not acceptable? Because you want to build an amplifier. You don't want to build an oscillator. So if your amplifier oscillates, that's not acceptable. That's not something you want, right? But many of the times, remember that when you'll be doing design projects, let's say if you take a graduate class and do a design project, more often than not, students come up with an amplifier that oscillates or an oscillator that just amplifies and does not oscillate. So it's kind of hard to keep a distinction between the two. And many times you'll see that you'll run into that problem because of the stability issues and because of the fact that your op-amp by default will have so many poles. So what is done in case of op-amp design is something called compensation. And now this is something that you'll learn in detail in eCircuits 2. It's not part of this course, eCircuits 1, but I just wanted to give you a brief idea about what compensation is. So compensation or pole splitting, it's also called pole splitting. What does that mean? That you have two poles, let's say you have P1 and P2 at these two locations. And for both the poles, your gain is more than 1. And we are saying that this is not acceptable. Why? Because it might create some oscillations. And we'll see why it creates oscillation in the next page. Now, what compensation or pole splitting does is that it takes these two poles and then pushes the left-hand side pole further towards left and the right side pole further towards right. So the pole that is at left, that is at a lower frequency, it pushes to even lower frequencies, and the pole that is at higher frequency, it pushes it to even higher frequencies. So that's why it's called splitting. You have the poles here, you try to split them apart. The low frequency one becomes more low frequency, the high frequency one becomes more high frequency. And the method by which you do that is called compensation, or sometimes it's called Miller compensation, based on the person who did that for the first time. We'll know the details in eCircuits 2, that how compensation is done and what are the equations that you should use for that. But right now it is suffice to know that this was the challenge, and that's why you want to do pole splitting. That's why you want to learn e-circuits 2 later on, right? So this will be a concept that will be taught later. But before that, I would just like to talk about some other concepts about gain crossover frequency, phase crossover frequency, and phase margin. So you know about poles and zeros, right? So for any system, there could be multiple poles, there could be multiple zeros. For example, for this transfer function, this is just an example random transfer function that I have written here, that on your numerator you have s plus a. So that means you have 1 0. And on the denominator, you have two terms, s plus b and s plus c, which means there are 2 poles. What are the locations of these zeros and poles? When you have s equal to minus a, if your s is equal to minus a, what will happen to the numerator? The numerator will become 0, right? So that's why at s equal to minus a, you have a 0. Similarly, when s equal to minus b or s equal to minus c, your denominator becomes 0. And that's the location of the pole. That's how the poles and zeros are defined. Now in the Bode plot, that is when you are representing a transfer function with respect to the frequency. So you are representing the transfer function, that is the gain and the phase of the circuit with respect to frequency. Now frequency, you can say it's my frequency f, or it could be angular frequency omega, which is nothing but 2 pi f. Okay. So it's usually represented in terms of omega when you are talking about a Bode plot. Now in a Bode plot, each pole adds an additional 20 dB per decade on the slope. So if you have one pole, it's 20 dB per decade or minus 20 dB per decade. If you have 2 poles at the same location, let's just assume that B is equal to C, right? So if B is equal to C, you have 2 poles at the same location. And then instead of 20 dB per decade from that particular frequency, you will have a slope of 40 dB per decade, right? So each pole will add a minus 20 dB per decade in the slope, right? So the slope will become more and more as you add more and more poles. And similarly, it will add a minus 90 degree phase shift. Why phase shift? Because you know that S is equal to j omega. And from your concept of complex numbers, you can find out the phase of a complex number, right? So if you have a complex number as a plus jb, right? What's the amplitude of that complex number? Square root of a squared plus b squared, right? That's the amplitude of the complex number. And what's the phase of the complex number? That is tan inverse b over a, right? So you can use since s equal to j omega, you can represent this, all those poles or zeros, just by replacing s equal to j omega. You can represent them as complex numbers. You can find out what's the phase or what's the amplitude corresponding to them, right? So whenever you think about a pole, it adds a minus 90 degree phase shift. Again, why? Let's just think about the case that you have one pole, let's say is 1 over s plus b. Okay. Now this can be represented as, let me divide the numerator and denominator both by b. So you have 1 over b at the numerator. At the denominator, you have 1 plus s over b, right? So I've just divided both the numerator and denominator by b. So what's the phase of this, right? So you just represent s as j omega. So I write it as 1 over b, 1 plus j times omega over b, right? Now you know that at omega equal to b, you'll have a pole, or omega equal to minus b, you'll have a pole. What would be the phase of this complex number? You know that a plus jb, if this is your complex number, your phase is tan inverse b over a. In this case, what would be the phase? The phase would be again tan inverse imaginary quantity over the real quantity. And you see that you have the imaginary quantity that is j times omega over d here, and you have a real quantity which is 1 over here, right? Since this entire part is in the denominator, your phase becomes minus of tan inverse omega over d, right? Again, basic complex number theory. So you don't need to think about it this much, but if you want, you can just go back to the theory of complex numbers and refresh these concepts. So this is the phase, minus of tan inverse of omega over d. what will happen when omega is infinite, when you have a very large frequency. This is minus tan inverse of infinity. What is tan inverse infinity? 90 degree, right? So you have a minus 90 degree because of the pole, existence of the pole at omega equal to b. Because of the existence of that pole at infinite frequency, you'll see an addition of a minus 90 degree phase. That's what I'm trying to get at, right? And again, it just comes from complex numbers. So nothing fancy. So each pole will mean an additional minus 20 dB per decade, and each pole will mean an additional minus 90 degree phase. So if you have two poles like this, you have P1 and P2. You have minus 20 dB per decade when you are at P1. After you reach P2, you'll have minus 40 dB per decade. The point at which your gain curve crosses the gain equal to 0 dB or gain equal to 1 line. So let's say this line, the x-axis, that represents that your gain is equal to 1 or gain equal to 0 dB. Why 1 is equivalent to 0 dB? Because 20 log 10 of 1 is 0. Right? So in terms of dB scale, this is 0 dB, or in terms of non-dB scale, it's just gain equal to 1. So the point where it crosses that gain equal to 1 or gain equal to 0 dB, it's called the gain crossover frequency, or GCF. Right? What will happen to the phase? You'll see a 90 degree, minus 90 degree phase difference at pole P1, and another minus 90 degree because of pole P2. Right? So because of the two poles, you'll see an overall 180 degree phase difference. The point where, or the frequency where your phase will change from a 0 degree to minus 180 degree, that crossover point is called the phase crossover frequency. Okay. And phase margin is defined as the phase at GCF minus 180 degree. So whatever phase you'll have at GCF, the gain crossover frequency, minus 180 degree, that's the definition of phase margin. What's the implication of phase margin? So in this case, you have a gain crossover frequency which is more than the phase crossover frequency. Your gain crossover frequency is on the right-hand side. This is your gain crossover frequency, and this is your phase crossover frequency, right? So your phase crossover frequency comes first, your gain crossover frequency comes later, right? This means that the phase margin will be less than or equal to 0, and it will mean an unstable system, right? According to the definition, it will be a less than equal to 0 of phase margin. On the other hand, if you had a single pole system, you have your P1 here, you have your 20 dB per decade slope, and you have your P2 here, right? After it has crossed the gain crossover frequency. So what is happening to the phase? You have a minus 90 degree phase because of P1, but P2 comes much later. P2 comes after the gain crossover frequency. So you get your minus 180 degree phase at a much larger frequency than your gain crossover frequency, right? So at this point, you have your gain crossover, and at this point, you have a phase which hasn't yet reached minus 180 degree. Now, according to the definition, phase margin is phase at the gain crossover frequency minus 180 degree, right? Or or I should say minus 180 degree. So it will become basically plus 180 degree. So I'll just correct this. So at this point, you have your gain crossover frequency. What is your phase at this point? It's something in between 90 and 180. Let's say it is at 135, minus 135 degree. So if you have minus 135 degree as your phase at the gain crossover frequency, so this is minus 135, and then you add 180 degree to it, so it becomes positive 45 degree, right? So if your gain crossover frequency is arriving earlier than your phase crossover frequency, you have a positive phase margin, which will mean a stable system, that there will be no oscillations. So what is meant by instability? Instability is oscillations. Why do we say that having a positive phase margin means that you have a stable system? Okay, remember that we have talked about this, that instability is oscillation, right? And oscillation happens when you satisfy something called a Barkhausen's criteria. What does Barkhausen's criteria say? That you have a positive feedback loop, and in the positive feedback loop, the phase difference is an integer multiple of 360 degree. And gain in the oscillatory loop is more than 1. What is the physical implication of that? Why do you see oscillation? Let's say you have this loop. You have an amplifier, you have some feedback circuit, and then you are feeding a portion of the amplified output back to the input. Okay. Now let's just assume that you have a sine wave, you had a sine wave at the input. So you amplified it. At the amplified output, let's just assume that this is a common source amplifier. So at the output side, you'll see 180-degree phase difference, right? Output will look like this. Then you pass it through a feedback network. And the feedback network may also add some kind of phase, because the feedback network could be an RC circuit. So it can add or subtract some kind of phase. After adding or subtracting the phase, at the input side, at this adder, if you see that after doing the feedback, whatever you see here is identical to whatever you had on the input previously, then you can cut off the input and have an infinite supply of the same signal in the loop over and over again. Why? Because you have a 360-degree phase difference, or a multiple of the 360-degree phase difference through the loop. Whatever was present at this point, if this had 0-degree phase, this point, let's say, had 180-degree phase, and somehow you create a feedback network that adds another 180-degree phase. So at this point, you have 360-degree, which is equal to 0-degree. 360 is equal to 0, right, in polar coordinates. So at the input, you have the same signal back. So if you cut off the signal now, if you are not providing any signal at this point, still you will see that there is an input present, which is this feedback input, which is exactly at the same phase as your original input. So again, it will go through the same loop, come back as the same input. Again, it will go through the same loop, come back as the same input. And again, it will go through the same loop, come back as the same input. So that's the concept of oscillation. That's the concept of the Barkhausen's criteria, that you had an input, but even if you have removed this input, something happens in the circuit that gets you back the same input again and again, again and again. Right? And what does that mean? You have oscillation. Right? Again and again, you are getting back the same thing. You are getting back the same sine wave. So even without applying any kind of input, even without providing any kind of power input or signal input to this is able to generate this output sine wave for an infinite amount of time. That's the definition of an oscillator. An oscillator keeps on oscillating even without any AC input to it. For amplifiers, you provide an AC input, you get an AC output. For an oscillator, you don't provide an AC input, you just get back the AC output, right? So a question: so are we sort of violating the energy conservation theory? No, right? Because the DC energy is getting converted to the AC energy for an oscillator, right? Even if you're not applying any AC input, it's the DC energy that gets converted to the AC energy, and that's what you see at the output. So the concept of oscillation is that you have to create a loop where there is 360-degree phase difference, or a multiple of the 360-degree phase difference, so that your input to the loop looks identical to the original input, even if you have removed the original input after some point. Right? The other condition that you need to satisfy is that the gain in the loop has to be more than or equal to 1. Why is this important? Why is this required? Let's say the gain is less than 1. Let's say the gain is 0.1. What would happen in each cycle? Every time you come back, every time you traverse the loop, your signal becomes 1/10. So after some time, you'll see damping. And because of that damping, your oscillation will die out. That's what you want to avoid in an oscillator. For an oscillator, you want to have a gain of, let's say, exactly equal to 1. Right? But then there are losses in the circuit. To compensate for those losses in the circuit, your gain has to be more than 1. That's why the Barkhausen's criteria says the gain has to be more than 1. But for an ideal scenario, even if your gain is equal to 1, you just get back the same signal again and again. Right? Because your gain is equal to 1, your phase is 360-degree apart. Which means that even if you have removed the input, you get back the original input again and again through the loop. Okay. Now we know that how oscillation occurs. Now let us go back to these plots. Okay. So what we said is that in this entire loop, we want to add one additional 180-degree. Right? So what you are really trying to do is that by adding that additional 180-degree, and you are trying to have a gain of greater than 1. That's when you oscillate. That's when you satisfy the Barkhausen's criteria. If you think about the Bode plot, when does this occur? When do you have an additional 180-degree phase difference with a positive gain. It happens in this scenario, right? When your phase crossover frequency is before the gain crossover frequency. Remember that on the left-hand side of the gain crossover frequency, your gain is more than 1. This is your gain crossover frequency. On the left-hand side of gain crossover frequency, the gain is more than 1. This is, let's say, 100 or 1000, something like that, right? So on the left-hand side of gain crossover frequency, you have gain of more than 1. And your phase crossover frequency is on the left-hand side of gain crossover frequency. Which means at the phase crossover frequency, where you have this 180-degree phase difference, you'll have a gain of more than 1. And that's when you satisfy the Barkhausen's criteria. And that's why you can see oscillation. So that's why this is your unstable system. The second case, this is where you design an amplifier. This is how your amplifier should look like. This is how your oscillator should look like. This is how your amplifier should look like. So you see that they are basically the same thing, just that the Bode plot is a little bit different. For the amplifier, when you have this 180-degree phase difference, when you are at the phase crossover frequency, so starting from here, you have 180-degree additional phase difference, and this phase difference actually comes from your feedback network. So when you have this 180-degree phase difference, your gain has become less than 1. So even if you are satisfying this criteria, Barkhausen's first criteria, you'll not satisfy the second criteria, and that's why your system will not oscillate. And that's called a stable system. Okay. So your amplifier needs to be a stable system, whereas your oscillator needs to be an unstable system. Right now we are studying amplifiers, so we are considering this case. Okay. And what is the phase margin for this stable system? You need to have a positive phase margin. Okay. And phase margin is this difference that from your 180-degree phase difference, however away you are. So let's say you are at minus 130 degree here. That means you have a phase margin of positive 50 degrees. If you are at minus 100 degrees, then you have a positive phase margin of 80 degrees. So on and so forth. Now you can prove, again from mathematics, I'm not going to prove this. This is E-circuits 2, that if you want to have a 60-degree phase margin, that this difference is 60 degree. That is, at the gain crossover frequency, your phase is, let's say, minus 120 degree instead of being minus 180 degree or anything else. So for a 60-degree phase margin, your P2, that is the location of the second pole, that has to be 2.2 times away from the gain bandwidth product, or from this point, from the gain crossover frequency, right? Remember, gain crossover frequency is your gain bandwidth product, right? Okay. So that's something that we have established. Now for a positive PM, this is something we have already discussed. If you have a positive phase margin, at PCF, your gain is less than 0, so it will not oscillate. It will not satisfy Barkhausen's criteria. So that will be one concept that we'll be using while solving the op-amp problems, while solving homework 8. Another concept that we'll be using is called slew rate. The slew rate means how fast the output moves for an ideal input. Let's say we're talking about an inverter. Let's just make it simple. Instead of talking about amplifiers, let's talk about inverters. What inverters do is that if your input is 0, your output is 1. If your input is 1, your output is 0. Right? So it's just the opposite of whatever your input is. Keep in mind that these are digital inputs we are talking about. That if your input is a digital 0 or a digital 1, your output will be a digital 1 or a digital 0. Okay, that's the job of the inverter. Now, the inverter cannot instantaneously change its output as you are instantaneously changing your input. So there would always be some kind of slew. Okay, there would be some kind of slope at the output. Let's say it takes a time t to for the output to reach from VDD to 0, which means the slew rate is nothing but VDD over t. Right? So the amount of voltage excursion that you need to support, so that is VDD to 0, and over how much time you are doing it. So over a time of t, you are doing it. So it's just a voltage excursion or a change in the voltage over a certain period of time. So that's what slew rate means. So now with this concept in mind, we can start looking at homework 8. We'll probably get about 5 minutes today, and we'll spend the entire lecture on Wednesday trying to solve homework 8. And also in the exam, it will be very similar. So what it is given here is that you need to design a 2-stage CMOS op-amp. Why two-stage? Because we know that the third stage is just a source follower, right? That's just to make your output impedance small. So that's why let's say we are just interested in the first two stages for now. I'm just assuming that you can always solve the third stage. That's a source follower. So these two stages are a Diff-Amp with current meter load and a common source. You have a Diff-Amp with a current meter load, and then you have a common source circuit. Note that the input to the Diff-Amp is given to the NMOS circuit. So this is an NMOS input configuration. And then the output of this is given to the PMOS of the common source. So this is the input of the common source, and this is the load for the common source. So this is an inverted version of what we had learned before exam number 2. In exam number 2, everything was NMOS input. Now things can be NMOS input or PMOS input. So your Diff-Amp was NMOS input, but your common source stage is a PMOS input. But you don't need to worry, all the concepts will remain the same. Still, the transistor needs to be in saturation. Still, the gain equations will be exactly the same. Nothing will change. It's just that instead of NMOS, you'll have to use PMOS. And as I have said, that when you're biasing it, just keep in mind, every time you use a PMOS, you use the absolute value. So the equation for saturation is VDS has to be greater than VGS minus VT, right? VDS has to be greater than the V over drive for an NMOS. For a PMOS, the absolute value of the VDS has to be greater than the absolute value of the V over drive. That's it. So that's how we bias a PMOS. But in this case, we'll not be asking you how to bias this. We'll just assume that you know how to do biasing. We'll just be asking about the AC characteristics, or we'll be designing it in terms of the AC specifications. Okay. Now, there is something that you see here which is new. This is called a capacitor that is used for pole splitting. So again, this will be part of e-circuits too, but we have discussed in brief that what does pole splitting mean and what does compensation means and why do we need it. You need compensation because you want a single pole system. You want only one pole in your op-amp. You don't want 10 poles in the op-amp, right? 10 poles may lead to instability. It may lead to oscillation, right? So to make sure that you have only one pole, we'll be using this compensation or the compensation capacitance, the Miller capacitance. And we'll just ignore it for now, that how do we design this, but we'll remember the formula that keeping CC greater than 0.22 of CL ensures that we'll have 60 degree greater than 60 degree phase margin. So again, something that we'll learn in e-circuits too. But for now, keep in mind that this CC, the value of the compensation capacitance, has to be more than 0.22 of CL, more than 0.22 of the load capacitance, so that you get the 60 degree phase margin. Now, but having a large CC, if you have a large capacitance, it will hurt something else. It will hurt your slew rate. Because now you need to, what is slew? What do you have a slew rate? Why do you have a slew rate? Right? You have a slew rate because, again, there is some RC delay. Right? So ideally, signal should look like this. Why does signal look like that? Because you have some kind of RC delay in the circuit. Right? And as you are increasing this capacitance, you are trying to increase this capacitance to get better compensation. But as you're increasing that capacitance, your slew rate will suffer. So that's the trade-off. So again, slew rate is given by I5 over CC. So if you're given the slew rate number, you can find out I5. What's the current that needs to flow through this tail transistor? That you can find out from the slew rate. And another thing that CC affects, the compensation capacitance affects, that's a gain bandwidth product of the op-amp. And again, these are three things that we'll be learning in e-circuits too. I'm not proving them here. One is, why do you need CC to be greater than 0.22 CL for a 60 degree phase margin? One is the equation for slew rate, which will be I5 over CC. And the other one will be the equation for gain bandwidth product, which is GM1 over CC. So these are the three formulas which we are not proving in this course. They will be part of e-circuits too. But for solving this problem, just for the sake of completeness, we'll use those formula. We'll learn how to prove them in e-circuits too. Except for these three assumptions, everything else we have learned in this course. Okay, so what is meant by designing? What we mean by designing is that you want to find out the aspect ratios of each of these transistors, which will help you meeting some specifications. Right? So you want to find out the aspect ratios, which are the W over L ratios. What's the width to the length ratio of the transistor? for each of these transistors, M1, M2, M3, M4, M5, M6, and M7. What would be the W over L ratio for each of these transistors? And that's something we'll discuss in next lecture. But before that, please go over the derivation and also the example problem that I have solved here, so that you have a fair bit of idea before coming to the next lecture. And we can, if you have like specific questions, we can discuss those in the next lecture. Okay. But I'll also quickly go through the derivation and how do we solve for each of the W over L for each of the transistors. Okay. Thanks, guys.